What I want to do is talk about some of the analytic methods for looking at exposome data and the challenges they present, and show you some results. So, you know, as a preamble, exposome, the word came from genome, right? They thought, well, let's take the same ending and stick it on expose, right? But if you have 1 million SNPs, they're not really correlated with each other. You can do 1 million separate regressions and correct for multiple comparisons and go to town. But the exposures in the exposome aren't like that. They're moderately and sometimes highly correlated with each other. And so the methods that we use have to be ones that can deal with that. And so that's what I want to talk about. So I want to give you a very brief introduction to two methods that are widely used for analyzing mixtures: weighted quantile sums and BKMR, Bayesian kernel machine regression, and then examples applying it to mixtures of air pollutants and sometimes air pollutants and temperature and other variables and health in the elderly. So let me start with, this is not a statistics talk, I'm going to give you a very heuristic explanation of what these are. So the basic idea of weighted quantile sums is, if I look at all of these exposures that I have, many of them have very different ranges of variation. Some of them may be a lot higher in concentration than others, and it's very difficult to analyze that kind of situation. So we want to convert them to being on the same scale. Now I could turn them all into z-scores, but the problem is I would still have outliers in all of these exposures, and I'd like to deal with that also. And so one good way to do it is to put them on the same scales by turning them into quantiles. And in my case, I use deciles, and that's because I have 10 fingers. If you have a better reason for why I use deciles, come and talk to me later. So the way this works is you divide the data into two parts. And in the first part, you calculate a weighted sum of the deciles for each of your exposures that fits the data best, right? So I explore all these different weights and I try to find the set of weights for different exposures, different PFASs, for example, that has the most correlation with the outcome. And then in the other part of the data, I use those weights to create a single variable, which is the weighted sum of all of these deciles. And now I have an index, one variable, and I can do a regression that gives me the overall mixture effect. So I get two things out of this. I get the overall mixture effect, and I have the weights, which are telling me the relative importance of different exposures in this exposome that I'm analyzing. So, for example, this is from an analysis we did looking at the effect of 15 PM2.5 components on the risk of hospital admissions for thrombosis in 11 US states. And so the overall mixture effect was a 1 decile increase in this mixture was associated with a 2% increase in the risk of thrombosis. If I look at the relative weights, so vanadium and elemental carbon seem to be the most important, and then copper and iron are showing up, and copper and iron are non-tailpipe pollutants from traffic, and EC is a tailpipe pollutant. So this is suggesting a traffic signal. Vanadium is not, that tends to come from heavy fuel oil combustion. And then I see things like sulfates and organic carbon, not important at all, okay, for thrombosis. So then we go and by this time we managed to buy the hospital admissions from a few more states. And so we have data on 14 states, all of the admissions. And we're looking at stroke. And you know, vanadium is nowhere to be seen, EC is nowhere to be seen, copper, iron, no, what's showing up is nitrates and sulfates. And then my favorite metal, lead. But a very different pattern. So then we looked at the Medicare population. So this is an elderly population, right? And we looked at mortality in the Medicare population using a mixture analysis, weighted quantile sums. And what you get for all-cause mortality in the Medicare cohort was zinc, organic carbon, nickel, some sulfate, EC, copper, nowhere, right? And it differs if you look at CVD deaths and respiratory deaths. All right? So now we looked at hospital admissions for non-respiratory infections. Okay, and what we saw was the overall effect was about a 11% increase in non-respiratory infections. And if we restricted to zip codes where PM 2.5 was below the recently set EPA ambient air quality standard, so they never exceeded that. EPA thinks this is safe, right? Then, guess what? The rate ratio goes up substantially. So the per unit pollutant effects are lower at lower doses. And then we see, you know, CNS infections, there's nothing going on there. UTIs are important, septicemia. But when I look at the weights, sulfates, nickel, all right, we saw that before sometimes. Copper is back. Iron is back. EC is nowhere. OC is less than nowhere, and nitrates. Okay. So, we said, well, why don't we turn this into looking not at individual components of particles, but at sources. So we used non-negative matrix factorization to try to identify factors which we could identify with certain sources and look at what the association was with the sources. And oil combustion, and vanadium comes in there, you know, is looking important. Coal burning, that's the sulfate, is looking important. So is, traffic. And that's what we find when we do it that way. So it looks like traffic, coal, oil combustion. So this is looking at another outcome, which is admissions of the elderly for depression. And here again, okay, we see sulfate, so that's showing up some. Other is the difference between the sum of the 15 components that I modeled and the overall PM 2.5, which I also modeled. So this is all the other stuff. And it seems to be important. And, you know, there's a little bit of a sign from nickel, EC, OC, nitrate. Here we put in NO2 and ozone as well as the particles. And so for depression, that's the picture that we're seeing. For bipolar admissions, sulfate still shows up, and NO2 is suddenly important for bipolar admissions. So this is a traffic pollutant primarily, but so is EC, and that's going nowhere. Vanadium isn't showing up, and neither is nickel. And for the schizophrenia admissions, sulfate and NO2 are back. Now we have some zinc and some EC showing up as well. Lung cancer. So again, this isn't in Medicare. And this is incidence of lung cancer. This is the Medicare Chronic Condition Warehouse identifies the first time a disease is mentioned in any diagnosis in their system, including physician visits, outpatient visits, nursing homes, as well as hospital admissions. And we required that people had to be covered by Medicare for at least 3 years before this first diagnosis showed up, to make sure that we were looking at incidence and not they'd already been diagnosed. And for lung cancer, vanadium and sulfate, nickel is now important. My favorite metal is important. EC, nitrate, you know, OC, not so much. The overall risk per decile increase for males is about an 8.2% increase per decile. For females, it was half that. So we were seeing effect modification by gender. All right. Now, that's throwing them all into one group. The problem with weighted quantile, a problem with weighted quantile sums, is that all the effects have to be in the same direction. That's not such a bad thing when you're looking at pollutants, because we think they're all bad for you. But sometimes when we're thinking about the exposome, we want to include things we think might be good for you, like green space that was mentioned several times. So one way around that is to divide the data into groups of variables. And so one variable could have positive signs, another group could all have negative signs, etc. So we had data from those 14 states I mentioned, and about 2/3 of the events I'll show you are in people over 65. So this is looking at cardiovascular disease, which is also an issue for people over 65. And here we're looking at absolute risks. So these are changes in the hospitalization rates per decile increase in each group of 4 exposure groups. And what are the 4 exposure groups? One exposure group is all the air pollutants. A second exposure group are winter and summer mean temperature anomalies. Anomalies comes from the climate change people. If you're an economist, you would call it an innovation. Okay? So this is the difference in this year's summer temperature in that zip code from the average summer temperature over the 20 years of the study in that zip code, and the same for winter. Then the third group are standard deviation changes, and then we put in interactions between air pollution and the temperature mean anomalies. And so here are the results. So for ischemic heart disease, air pollution is bad for you. Warming, we flipped the sign of the winter temperatures so that a higher number would be bad, whereas normally warming in the winter you might think would be good, but in the summer bad. So air pollution bad, warmer temperatures good. And we did a study 20 years ago looking at Medicare where we found that the risk for heart disease hospitalization just went down with increasing temperature. It wasn't U-shaped like we see with mortality. So I guess that's not a shock. The standard deviation didn't do much, and the interactions were positive. So warmer temperatures, there was an additional effect of air pollution above and beyond what we saw just for the air pollution effect. And the pattern is the same for all four outcomes, although the absolute magnitudes differ some. So you can do these group weighted, and we could have put in various green space measures, but we didn't get around to doing that. Next time. And what were the important variables? Well, for ischemic heart disease, sulfate was the most important. Ammonium goes with the sulfur and the nitrate, but mostly the sulfate. NO2, and then EC and nitrate and OC and ozone. But sulfate and NO2 seem to be the winners here. Minus winter mean and summer mean temperature were about the same. The standard deviations were about the same. But whereas the overall effect of ozone had a relatively small weight, like about 8% of the total effect of air pollutants, the interaction with summer mean temperature, was even larger, and so that adds up in warm years to a bigger ozone effect, and the same with OC, whereas, the sulfate interaction is not really doing that much compared to the main effects. And cerebrovascular disease, pretty much the same story in terms of the air pollutants and the temperatures. For the interactions, all of a sudden, NO2 and sulfate, interacting with temperature seemed a little more important, but everything was sort of kind of similar. So that's a little different. Heart failure, same basic idea, and arrhythmia. So we can do these kinds of models and try to break apart the exposome into sections and possibly their interactions. Bayesian kernel machine regression. Let's just remove the Bayesian part for a minute. That's just this iterative way that we estimated, and talk about kernel machine regression. Kernel machine regression is a variant of support vector machines which were invented by Vladimir Vatnik in the 70s. So, and I will give you a heuristic explanation because you don't want to see that. So, basically, imagine I have two variables, x and z, and they predict my outcome y in some way. Okay? Now, y may depend on them non-linearly. So I might want to put in x squared, x cubed, x fourth, x fifth. Same with z squared, z cubed, x, z, x squared, z, x cubed, z, x, z cubed, etc., etc. All of a sudden I have, from two variables, a huge number of variables. Right? Too many. So, first of all, we transform them into something that's called a Boole space. I've now said that. I will not say anything more about it. And we put them into a mixed model. Because what a mixed model does is you can say some effects are random. Like if you were fitting a longitudinal analysis of multiple measures in a person, you would have a random intercept for that person that captures the fact that their lungs on average are bigger. And that's true for every measurement you make compared to the average, right? So we have a random intercept for each of these variables. And the random effects in a mixed model get one. And so that is a way to create a method for putting all of these exposures in together and getting an estimate that doesn't have to be linear and can incorporate interactions for the effect of the mixture. Okay? That's the upper level idea. Okay? And kernel, because what that mixed model does looks a lot like something called a kernel, and I'm not going to go into that. So here's what happens when we do it. So this is a study from the normative aging study, which is an aging cohort who were about 75 years old when these measurements were taken, and they live in the New England area. And so what you're seeing here is the overall effect by quantile of the mixture. And you can see for serum uric acid as the mixture quantile goes up, uric acid goes up, the risk of chronic kidney disease goes up, and there's a bit of a drop in GFR, but nothing with BUN. Okay? That's the overall effect. And then we get these non-parametric smooth dose response curves for all of the components, and they don't have to all be going in the same direction. So for chronic kidney disease, you can see for sulfur, it's clearly going up, almost linear. Black carbon is a little non-linear and a little protective, nothing going on with aluminum. Silicon, a little bit of a risk factor. You know, for uric acid, there's a slight increase with black carbon, decrease with calcium, increase with my favorite metal, and that's what you can see with these different things. And then I could ask the programs to draw this curve, let's say 3 times, once holding everything else at the 25th percentile, once holding all the other pollutants at the 50th and once at the 75th. And if there's no interaction, the curves will be parallel. And if the curves are diverging, then that tells me there's an interaction. Okay? So all this EKMR can give you. And it dies when you hit about 1,000 observations. It just takes really long to run because it's a Bayesian program. And so we have developed a fast EKMR algorithm that we were able to run on 900,000 birds, in Massachusetts. So we think we beat that problem. But its package is not quite ready to get posted on frame. So here, this is not air pollution, this is heavy metals in toenails, again in the normative aging study, and looking at the effect on QT interval, corrected QT interval, and you can see these are the same day, 1 day moving, a 2-day moving average, 3, 4, no, 1 day before, 2 day before, 3 day before, 4, 5, 6, and 7 day lag. And you can see there's clearly a significant increase in QTC associated with lead and maybe with nickel, and not really for the other metals. So, sorry, this is not toenail metals, this is the air pollution. Okay, so we can use EKMR for that. All right, so we have these two methods, and there are a couple of simpler methods that people have used. So, for example, if I stick to 3 major air pollutants, I can look at the incidence of dementia in the Medicare cohort, again using this chronic condition warehouse. So they have to have not had any diagnosis or mention in their health record of dementia for at least 3 years before the date. And we see associations with PM and NO2 and a protective effect of ozone, which is probably because ozone and NO2 tend to be negatively related. And then this is the same thing for Alzheimer's. And when you go from single pollutant models to a 3 pollutant model, nothing happens to the PM effect, but the NO2 goes down a little, and the ozone goes from nothing to slightly protected. So if you don't have too many things, you can still try a multi-pollutant model, and you can also look at the dose response curves, which are reasonably linear for PM and for NO2 for dementia, although it flattens out for Alzheimer's disease, and then there's nothing going on with ozone. And the last one I want to show you is a canonical correlation analysis between metals, and these are toenail metals, arsenic, cadmium, lead, and manganese, and various extracellular microRNAs. So these are from extracellular vesicles. Again, in the normative aging study, and when we adjust for covariance, so let's look at this one. These are the microRNAs that show up, and it's essentially all being driven by cadmium. So, conclusions. WQS and EKMR work. I think their estimates of the overall mixture effects are pretty good. sometimes it's sulfate, and sometimes it's vanadium, and sometimes EC is really important, and sometimes it's completely unimportant. And you might say to me, well, these are all different health endpoints. Yeah, but you know, these particle effects, you know, seem to be driven by reactive oxygen species and inflammation, and they're related to all of these, you know, outcomes. And so I mean, sulfate showed up more often than anything else, so it's probably a worse than average actor, but I think that looking at these weights, we need to be really careful because I think they're bouncing around too much. Because in the end, when you have a bunch of correlated exposures, you know, there is no magic in statistics. Right? It's hard to separate them out. And so that's my overall conclusion.